Okay, time for today's lectures. Again, I thank you for your participations. And in particular, I want to tell you how thankful I am for being here on time, which is not easy considering the weather is getting colder and colder, and it's getting more and more difficult to get up early. Okay. Now, in the beginning of today's lecture, we will talk about what we left off last time, rule locus methods. Okay. Now, let's first consider this feedback control system. Okay. Now, here we have a parameter k, which is the game. You can think of it as a game of the loop transfer function. Okay. Now, k is a parameter whose values is weighted to be determined. All right. If I have a k here, then the closed loop, the transfer function of this closed loop system will become this. All right. We saw this representation before. Hopefully everybody know where does this result come from. All right. Now, what is rule locus? Let's first understand what it is, and in particular, its relationship with these parameters, which is weighted to be determined. The rule locus method is a powerful graphical tool or used in control system engineering to see exactly how a system stability and performance change as you adjust one main knob, usually sensitive game. All right. So it's basically a graphic tool to help you understand the impact of K, okay, on the stability as well as performance. As a matter of fact, the rule locus is a plot that shows the path traced by the closed loop poles as you adjust the system gain. So this sentence is clearly specify what rule locus really is. Rule locus is essentially a trajectory of the poles. Okay, why do we have a trajectory for poles? The answer is because we have different values of k. When you set k equal to 1, poles are located in certain region. If you, let's say, increase the value of k, poles will be relocated. Okay, so if you incrementally increase k, let's say from 0 to 0.1, 0.2, all the way up to whatever value you want it to be, you will see the location of the pole also changed gradually. Okay, and in the end, okay, it forms a trajectory or it forms a path, and the path might look something like this. Okay, let's say in this particular case, initially when k is 0, we have 3 poles. Okay, this is the system of interest. This is the system under consideration. All right. So initially we have 3 poles for the loop transfer function. Initially we have 3 poles. X equal to 0, x equal to -1, and x equal to -2, which are located here. All right. But if, remember, this is the transfer function for open loop control system. Now, if you increase the value of k, all right, the roots of the characteristic equation of the closed loop system, that is the poles of the closed loop systems, will change. Okay, well, will be shifted to different locations. For example, when I increase the value of k, let's say to 1.383, then the poles, this pole, move from here to here. If I increase the value further, let's say to 6, then this pole will move to here. This is the new location of this pole when system gain parameter k, when the value of the system gain parameter k is 6. Similarly, these two poles, the location of these two poles will also be shifted. For example, one will go this way and the other will go this way. When the value of k, let's say, changes from 0 to 1.383, then the location of these two poles are shifted to here and here. If I continue increase the value of k, let's say this time to 6, then these two poles, the locations of these two poles will be here and here, okay? And this particular value of k is critical because if you increase the value of k further, the poles, the location of the poles will be on the right-hand side of the complex plane. And the system will therefore become unstable, at least asymptotically unstable, okay? So this is the red line we cannot cross, because if we cross that red line, everything will explode, just because system will become unstable. So rule locus is, in the beginning, as we said in the beginning, a graphical tool, because it helps us visualize the impact of k on pole locations. All right. Now, there are many different rule locus. We'll come to that later. But now, drawing, tell you how to draw those rule locus is not what we want to do. Why is that the case? Because you can always ask computers to do that for you. All right. But nevertheless, we still have to know how to draw those rule locus. That is the principle behind rule locus. Okay. The rule locus method is based on the characteristic equation of closed loop system. All right. So the poles are always the roots of this characteristic equation. All right. So now, if this, so we need to find S to satisfy this characteristic equation. If this equality has to be true, then this has to be true. That is, the product of k and g and h has to be -1. But that is just one condition. We have another condition, all right? Again, let's look at this characteristic equation. For example, it can appear something like this. Well, this GH is this, all right? As you can see, we have m zeros, we have n poles, and this is the system parameters, gain parameters that we need to determine, all right? As I said before, for the poles to be located on the rule locus, the first condition is this has to be -1, and the other, which means its magnitude has to be 1, and which means this angle. Here you see magnitude and angle, which means we are viewing the locations of the poles by its polar coordinates, okay? So we want the pole, since this is -1, which means in the complex plane, remember this is the real part, this is the imaginary part. It is located here. Well, its is distant, the location of this particular pole, its distance from the imaginary axis is apparently 1, all right? Since we are using polar coordinates to represent this pole, we have to know the angle, which is 180 degree or minus 180 degrees, okay? And it can be, I can go around for one more circle, which means it can be positive for 540 degree or minus 540 degree. Nevertheless, in the end, the general conclusion, the general solution is that the angle has to be this, which means it's the up multiple of 180 degrees plus and minus 180 degrees. Okay, so the magnitude condition is that this has to be true, and the angle condition for the rule locus is this has to be true. Where here case is equal to 1 or positive minus 1, positive minus 2, all the way up. All right. Okay, and here are formulas that we need to know in determining the for determining the rule locations. All right. Now, instead of reading these texts, let me just give you one simple examples. That is, how do I determine the magnitude and the angle of the rule transfer function? Okay. Remember that our attention for the time being is not on the characteristic equation. Our attention for the time being is on the loop transfer function. All right. We are focusing on loop transfer function. Okay. So, for example, this is a loop transfer function of a feedback control systems. Now, to determine its magnitude and to determine its angle, we can use these two plots to help us. Okay, here I have 1, 2, 3, 4. I have 4 poles, 1 zeros, and the location of minus P1 is here. Similarly, the location of minus P2, minus P3, and minus P4 are all represented by these cross signs. And the circle here represents minus Z1, which corresponds or copes to the 0. Now, to determine this, its polar coordinates, all I need to do is set out a vector connecting minus Z1 and X. And this distance represent B1, represent the magnitude of X plus B1. All right. Now, similarly, for this term, all I need to do is draw a line between S and minus P1. And by doing so, I set out a vector. And the length of that vector is, for example, A1. So I put an A1 here in determining the magnitude of GH. So I can do the same thing for this pole, and this pole. And that is exactly what I do. All right. So determining the magnitude of the loop transform functions can be is achieved by identifying the lengths of all these vectors. Similarly, the next thing we want to do is to determine the angle of the loop transfer function. all right? So again, we go back to these lines. We go back to these vectors. But this time, the focus is not on the length, but on the angle. For example, the angle here that of this vector, which connecting x and minus v1 is phi1. So what we have is phi1. Similarly, the angle here, that is the angle for the vector that connecting x and minus p1 is zeta1. So we have minus zeta1 here. Why do we have a minus sign? Because the pole is on the denominator, right? Okay. So this is how we get our angle. This is how we calculate our the magnitude for the loop transfer function. All right. So if S is indeed on a point of the rule locus, then this has to be, let's say, this, or this, or let's go 180 degree further, this, right? Now, and if, again, the pole is located on the rule locus, then this has to be true, all right? So this is the basis of the method that we used to determine the trajectory of the pole. That is to determine the rule locus. Okay. After understanding this idea, okay. Now, as I said, this is the one example which shows that how poles varies with the game. All right. Now, of course, this is just one example. If you go to the textbook of automatic control, you will see a lot of rule locus. This first example is the example we just inspected, which involved 3 poles. This is another example. The difference between these 2 examples is that here I have 3 real poles in the open loop. Here I still have 3 poles. I'm still considering a third order system, but instead of have 3 real poles, here I have a pair of complex conjugate poles for the closed loop. I'm sorry, for the open loop transfer function. Okay. In this case, I have 4 poles. All right. So there are many variations. Okay. For all. So here, this plot considered all types of, as many types of variations as possible. For example, this is still a second order system, but here we have a pair of poles and only 1 zero. In this series of graphs, there is no zero whatsoever, but here we see 0 pretty much everywhere, okay? Now, from this rule locus, it gave you a pretty good idea what you can do up to the location, to the relocation of the poles if you only have one parameter that you can adjust, okay? So there are some limitations, but at least it helps you understand the strengths and the limitation of adjusting K in relocating the poles of the closed loop system, all right? Now, think about it. What does feedback control system really do for us? The fundamental change made by feedback control is it alters the transfer function. Initially, the transfer function is this. By setting up a feedback loop, I change its transfer function, which means I alter its system dynamics. And one governing factor for system dynamics is the pulse, right? So locating pulse on the right region is often a very important issue in controller design. All right. All right. That's all we need to do about rule locus. Now let's switch our attention. Move forward. Okay. Let's move forward to another very important topic, which is about gate margin and phase margin. Before formally introduce the definition of gate margin and phase margin, let us first clarify why do we want to do that in the first place. When it comes to the performance of the control systems, we need to come up with some measures to characterize how good a control system is. Generally speaking, as I told you before, these performance indices or measures can be classified or divided into 4 different categories. The first category is about accuracy. Okay. If you want a room temperature to be 25 degrees Celsius, it better be 25 degrees Celsius. At least the difference has to be as small as possible. So for accuracy is one considering factor. And the other thing is a fundamental requirement is stability. Whatever I do, the first thing I want to make sure is that the output of the system will not explode, will not diverge, will not increase without any limit, because it will cause disasters. Okay, so stability is another issue. And the third thing is, of course, speed of response. In setting out a control system, of course, I want to get things done. I want a system output to be behave as the way I want it to behave. All right, but that is one thing. But another thing I need to consider is how long it will take for the closed-loop feedback system to produce an output that I really are satisfied, that may be satisfied. Okay, how long will it take? Okay, if it take forever, that is intolerable. I cannot stand up with that. I want to get things done as fast as possible, because in industry, speed is usually equal to productivity. And productivity is always related to cost. High speed, high productivity, lower cost, right? Now, accuracy, stability, and speed of response are all very easy to understand. But there is another issue that requires our full attention. That is robustness. What do I mean by robustness? I mean the performance of the system has to be robust. That means the performance of the system, whether it's accuracy or stability or speed of response, we want the feedback control system when it comes out to those measures. We want to set our feedback control system to be insensitive to uncertainties, right? Why do we want to have feedback control system in the first place? Why not just use open loop control? Because we want to use feedback control system to deal with uncertainties. okay? And uncertainties are usually unpredictable. We wouldn't know what it is until everything comes online, all right? So it is very unpredictable. But when designing a controller, we always assume we usually assume we have a model. And based on that model, based on the parameters of that model, we design our controller. We locate, we place the pulse to the region that we think it will give us satisfactory result. However, the model of our systems, which has been used for the code to design the controller, might not be the same, okay? And there are, in addition to parameter variation or modeling inaccuracy, we also have other types of uncertainties, such as input disturbances, okay? Those are also, those input disturbances are also uncertainties, okay? Now, we want our feedback control system, okay, to be insensitive to those unpredictable factors. And that is what gain margin and phase margin is all about, okay? Now, understanding of the motivation behind gain margin, after understanding the motivation behind gain margin and phase margin, the first thing I want to do is define gain margin and phase margin. Now, remember, here, like before, in discussing rule locus methods, here, this is the body plot, body diagram for the loop transfer function, all right? Not the transfer function of the closed loop system. No, it's the loop transfer function, okay? For example, in this case, in discussing the rule locus, our loop transfer function is, of course, this. This is the loop transfer function, which is the product of this and this. Okay, the product of all the subsystems, all the transfer function of the subsystem appear in this loop. All right. And the transfer function of the closed loop system is this. All right. So they are not the same. They are different transfer functions. Keep that in mind. So in defining phase margin and gain margin, we are talking about, okay, we are talking about loop transfer function. Now, here, what we have is a body plot for the loop transfer function. This is the magnitude plot. This is the phase plot, okay? Now, the first thing we need to do is to identify gain crossover frequency, okay? That is the frequency where the gain of the loop transfer functions becomes 0 dB, all right? And after locating gain crossover frequency, I will go down, and go down to see at the gain crossover frequency, what is the phase of the loop transfer function. And the next thing I need to do to determine phase gain is I need to find out how far away is this point from the minus 180 degree, all right? And the difference is what we call phase margin, all right? So that's the definition of phase margin. Now, let's go one step further. What is the definition of gain margin? Now, to define gain margin, the first thing that we need to do is first identify the phase crossover frequency. That is, we need to go to the phase plot and identify the frequency where the phase curve has an angle of minus 80 degrees. After locating that so-called phase crossover frequency, we go up and check in this particular frequency, what is the value of the gain in terms of the dB of the Lou transfer function is. And then we identify this difference, okay? That is the difference between this dB value and 0 dB. And this is the gain margin, okay? Now, in this case, we have a positive gain margin. We have a positive phase margin, all right? Now, let's go one step further, okay? Now, this is a session that has positive gain margin and positive phase margin, which means that this session is stable. I will tell you why this session is stable in later, all right? However, for this loop transfer function, the gain margin is negative because the gain of this magnitude to plot at a phase crossover frequency actually has a positive dB values. It is larger than zeros. In order for the system to be asymptotically stable, this value has to be negative, not positive. Similarly, here, when we inspect the phase plot, we also see a negative phase margin, which means the system is unstable, all right? So finding out whether gain margin and phase margin are positive or negative give us another way to determine the stability of the system, okay? Now, let's describe the basic idea of gain margin. Gain margin and phase margin are measures about how stable a feedback control system is. That is, it gives us absolute measures to characterize the relative stability of the system. They tell us how much room we have before the system becomes unstable, okay? Now, if a gain margin is 50 degrees, okay, and for one system, and the other system, let's say its gain margin is 30 degrees, then it is plausible to say, it is actually correct to say this system can tolerate more uncertainties than this system. That is, this system has more room when it comes to the consideration of stability, more room for uncertainties than the other system who has smaller phase margin, all right? Now, let me be more specific because after all, we have two measures. One is gain margin, the other is phase margin. Gain margin reflects how much we can increase the system gains before it starts to oscillate or become unstable. So it represents a tolerance to the uncertainty of system gains, all right? Phase margin reflects how much additional phase lag delay the system can tolerate before it becomes unstable. So in essence, gain margin represents tolerance to change in system strengths. Phase margin represents tolerance to change in system timing, all right? Now, here, I just give you the facts on the impacts of gain margin and phase margin. I have not yet told you why these conclusions are true. And that is what I want to do next. Let's go back to this diagram, which is a block diagram of a feedback control system whose transfer function is this. And we also this slide before, right? Now, based on the idea that we used to plot rule locus, we can now use that idea to understand where do phase and gain margins come from, all right? Now, a system becomes unstable when the characteristic equation has roots on the imaginary axis, all right? I'm sorry. Just like this figure, who has this loop transfer function, all right? Here, as I told you, when I increase k, the location of the pole move to different places, okay? And here, when k, the value of k increases to 6, this poles, at least 2 of the poles, are located on the imaginary axis. If I go one step further, then the system will become unstable, all right? So that is exactly the case that we are considering when we study the gain margin and phase margin, okay? Let me go back to this sentence. A system becomes unstable when the characteristic equation has roots on the imaginary axis. Therefore, the boundary or the verge of instability is found by evaluating the root transfer function at x equal to j omega. Okay, so let's say x is now, for example, as in this case, instead of on this position, let's assume S is located here, all right? Okay, so once S located here, the system is on the verge of instability, on the boundary of instability, because if you increase the value of K, no matter how much, the system will become unstable, all right? If that is the case at the verge of instability, again, you know that characteristic equation has to be this, all right? We saw this before, all right? Remember, here, x is equal to j omega, because we now assume S is on the verge, in the verge of instability, all right? And -1, if you use polar coordinate representation, is actually, it has a magnitude of 1 and it has a magnitude of plus pi or minus pi. That is the reason why we -1, I'm sorry, 1 correspond to gain crossover frequency, because if the gain is 1, then is dV value is of course 0, all right? Okay, if in this case the phase happen to be -180 degree, then the system is in the verge of instability. However, when system has a gain, root transfer function has a gain of 1 and therefore has a dV value of 0, the system's, the phase is now 180 degree. But for example, -150 degrees. So the poles are not yet located on the imaginary axis. You still have 30 degree of room, a 30 degree of phase angle tolerance. And this tolerance is a room to tolerate the impact of uncertainties on phase response, all right? Similarly, the reason why we define phase crossover frequency as the frequency where the phase angle is minus 180 degrees. Is because in the verge of instability, the angle is this, which happens to be when the angle is minus pi, happens to be minus 180 degree, all right? And if in this case, the gain is 0 dB, which the dB value, the value of the magnitude plot of the body diagram is 0 dB, which means the gain is 1. Then the system is in the verge of instability. However, thank God, we still have some room before I reach the boundary of instability. And this room is what we call positive gain margin. And it therefore characterizes the tolerance of the closed-loop feedback system to change in system strengths, which means that let's assume this is the body diagram of the loop transfer functions. And this, of course, come from the system model I use, come from the G I choose, come from the H I specified for the system. However, the real G might not be the one that I specified. For example, the real G can be something like this. It's an additional factor, which I did not consider in designing the feedback control system. So the real body diagram, when it comes to the magnitude plot, may not look like this. It may look something like this, or it may look something like this. In any way, it might vary. It might not be the same as this curve, all right? Why? Because uncertainties, all right? And this represents the tolerance to the variation of the magnitude plot of the body diagram. And the source, the reason for those variations is because the existence of uncertainties. All right? So let's first look at one uncertainties, that is the value of K, all right? Let's assume this is my transfer function. This is the loop transfer function, okay? Let's assume that initially I assume K equal to, K equal to 1. But in reality, K may not be equal to 1. Let's say K is, in reality, is 2. So in that case, when K is equal to 1, I created these two plots for my body diagram of the loop transfer function. This is the magnitude plot. This is the phase plot. Now, based on the definition of phase margin and gain margin, okay, I identified that the phase margin for my system is this. The gain margin for my system is this. However, since the value of K is not 1, but 2, then the magnitude plot, the plot will be elevated, okay? The shape of the curve will not be the same, okay? Because all I do is increase the gain, all right? So the curve will move upward, okay, due to the increment of K. Now, if this is the case, what would happen is that originally the gain crossover frequency is here, but due to the increase of the value of K, the gain crossover frequency changed from here to here, all right? So by definition, the phase margin becomes this, which is smaller than what it was. Similarly, although the phase crossover frequency has not been changed, but at the phase crossover frequency, due to the elevation of the magnitude plot, as you can see, the gain margin also is smaller than what it was, because before the increase of the value of k. All right. So if I increase the k, the amplitude spectrum, I should say the magnitude spectrum elevates, and gain margin and phase margin, as demonstrated in this figure, all become smaller. Okay. So this is also in agreement with this result. As you can see, when you increase the value of k, the poles started, at least these two poles, start to move, start to be shifted to more unstable region. All right. Okay. So the results from the root locus and the result from the body diagram are in good agreement. All right. Now let's look at another example. Okay. Now this is the example that we are considering now. Okay. Again, here is a k whose value is left to be determined. All right. And initially, let's say k is equal to 10. Then the gain margin is 8 dB, and the phase margin is 21 degrees. If you increase k by a factor of 10, all right, that is the value of k increases from 10 to 100. Then the gain margin reduces from 8 dB to minus 50, but I'm sorry, to minus 12 dB, okay? A 20 dB reduction, all right? Why is that the case? Because 20 log 10K is, 20 log 10K, all right, is 20 log plus 20, all right? Now, the phase margin also reduces from 21 degrees to minus 30 degrees. So because the large gain, the system switch from a stable system to an unstable system, all right? So increasing loop gain reduces both gain margin and phase margin because it raises the body magnitude plot, shifting the gain crossover frequency to the high, shifting the gain cross to higher frequencies, where the phase lag is larger, and thus phase margin decreases, right? Here, the phase lag is larger because compared to this point, this new point is more negative, all right? Which means it has larger phase lag. I'm sorry, let me turn off my mobile phone. I apologize. All right. Okay. This is the formula that I just wrote. Okay. I increase the value of k by 10. Then when it comes to the dV values, the dV value actually increases by 20. All right. Now, let's look at phase margin versus damping ratio. Let's use second order system. Let's investigate the second order system. All right. Now, let's assume here, this is a system under we are considering, okay, that we want to consider. Okay. Now, for this closed loop transfer function, its for this feedback control system as a whole, its transfer function is actually this second order system, all right? But remember that when defining or specifying phase and gain margins, our focus is not on the transfer function of the feedback system, but on the transfer function of the loop, but on the loop transfer function. Okay, let's take a 10 minutes break.